It's all good? Okay, great. So what I'm going to talk about today is actually a project funded by NSF. It's about this autonomous modular public transit service. So I'm going to explain what that means. But before I do that, I want to acknowledge my PhD student Xing Chen, and he's actually the one that's doing all the work, and this is part of his PhD thesis. And I'm simply here to present on his behalf. So all right. So just want to acknowledge this is funded by NSF, and it's actually a collaborative research between UIC, which is the lead, and I'm the PI on that, and also Northwestern with Professor Marco Nair. And so I'm gonna, before I get into what this research is about, I want to introduce some background information about this research so you can understand better what it is. So this technology about autonomous modular vehicle technology, or what we call the AMVT. So what I'm going to do is I'm going to play a video. It's about less than 3 minutes video. Bear with me to introduce this AMVT. All right, I think that's it for the video. So what did you see in the video? Oops, sorry. Should be the next. So what did you see in the video? So mainly there are two services that can enable by this AMVT technology. One is in the passenger transportation side, which is the transit service. And the other one is actually the last mile delivery side of things. But today's talk, I'm going to focus on the passenger side of the service, which is the AMVT-based public transit service. And so the majority of my talk is focused on the fixed route transit service enabled by this AMVT technology. But if I have time, and which most likely I won't, so I hope I can also get into this on-demand ride-sharing system that's enabled by this AMVT as well. So we'll see how it goes, okay? And so for the fixed route, AMPT, so it stands for the Autonomous Modular Public Transit Service, right? So really the motivation from this is we know that especially in the US, even in Chicago, which has the second largest public transit system, the ridership is very low, okay? So on average, you're looking at the statistics, it's about 10% to 12% of load factor. So it's very low ridership in transit service in this country, unlike like in Asia or the European cities. So, and this problem has obviously worsened by the pandemic, right? So, in fact, this proposal was motivated when I was in lockdown in Chicago. So I live in the near north side of Chicago. So I see the CTA buses. CTA stands for the Chicago Transit Authority. So the buses are running on streets, but they're empty because nobody's riding the bus at time because of the virus and so on. So it's like, wow, that's a waste of resources because no one is riding the bus, but because they still have to provide a service. So it's a waste of space and resources. So I said, how can we better utilize the resources so it's not wasted, right? So then I saw a video about this kind of a prototype called the AMVT, autonomous modular vehicle. And then it just dawned on me that, you know what, if we can customize the vehicle capacity in real time, in route, that can really make use of the resources much better, right? So when you don't have enough passengers in the car, you don't need a big bus, like 60-seat bus. That's a waste of space and resources. So we can just send out smaller vehicles and to meet the demand. But when it's a peak hour, then we can send out bigger vehicles, right? So that's where the idea really came from. And so I started looking into this AMVT technology, and obviously by its name, it has two unique features. One is the autonomy, right? Because it's autonomous, meaning driverless. And the other one is modularity. So the focus of this research is actually on the modularity feature, not so much on the autonomy, because we kind of take that as the, so it's that, okay, it's autonomous vehicle, it's driverless, but what can the modularity bring to the public transit service? So that's really the focus of this study. So as you can imagine from the video, so what this modularity really brings is this pod train forming and breaking off. So you see in the video, they can in real time in route forming a train of pods. What we call each of these vehicles we'll call it a pod. So you can actually form this train, so of different length in real time, or you can also break off this pods in real time. So because of that, and also it's shown in the video if you pay attention, so passengers can actually transfer in route without getting off the pod train, because they can go from one pod to another pod. And if that pod goes to their final destination, so they don't have to get off the pod train in order to transfer, because the pod can just detach from the rest of the pod train and go off to the final destination. So that's what we call the in-route passenger transfer. So that's really the unique feature of this AMVT-enabled transit service. Okay, so then our research objectives are really, this is a relatively futuristic idea because none of this has been in implementation in real world operation. So it's a proof of concept. So we want to see that, well, it's a nice technology. It has a lot of potentials, but does it really work in reality? So that's why we say, well, let's look into the feasibility of this AMVT service. And here we define the feasibility very narrowly in terms of the cost, the agency cost, as well as the passenger cost, okay, and unit of time. So we're not looking at any other feasibility, because people, when you talk about feasibility, that can be a lot of things. Operationally speaking, in terms of maintenance, in terms of infrastructure requirement, all these things, but we're not looking at all these things. We're basically just look at, well, in terms of the cost, from the agency's point of view, from the passenger's point of view, is it compatible with the existing the transit service, right? So if it's more costly, obviously, it's not a good alternative to the existing system, right? But if it's compatible and even competitive in terms of the cost, then that's a potential. So I also want to point out that because of this modularity, so this pod joining disjoining is a unique feature And this in-route transfer, really this represents the major departure from the traditional transit service literature, okay? Because the traditional transit, you don't have this kind of operations. And so the challenge becomes, how do we model that joining, disjoining, and the in-route transfer in a transit service enabled by this technology. So the way we answer this question is to have this study design. So we basically have the base scenario, which you assume the traditional fixed route, fixed size vehicle fleet, right, bus fleet. And we consider two demand scenarios, homogeneous demand scenarios, and the heterogeneous demand scenarios. So these are the P1 and P3. And then we also consider for the proposed AMPT, again, this is a fixed route scenario, okay? So for the AMPT, so we also consider the two demand scenarios. P2 is the homogeneous demand, P4 is the heterogeneous demand. So you have P1 compared to P2 and then P3 compared to P4. So everything else is the same, but one is using the fixed route, the fixed bus fleet, like the traditional setting, and the other one is using this AMVT technology, the plots to form plot trains and in-route transfer and so on, right? And then we say, okay, so in terms of the network, so we consider at the network level, because to really evaluate the feasibility, looking at one route doesn't really it's not very meaningful. So we have to make it at a network level. So we use a very simple network. It's a grid network. And this is actually adopted from this paper, right? So it's a grid network. So it's actually very much like the Chicago network. The Chicago street is very much this grid network. And then what you have here is the blue lines are the transit lines. And then it's not very good, doesn't really show. So in between, there's actually a very light gray lines. These are the streets. So basically the transit lines are running on every other street in this network. And then this is the size of the network, right? And then this is the spacing of the transit lines. And then we also assume each intersection is a bus stop, okay? So between the perpendicular lines. So each of this intersection represents a bus stop. Okay, so that's, yeah, so this still not showing very well, but that's okay. Okay, so then just like any modeling, we have to make a lot of assumptions, especially this is a relatively futuristic scenario. So we have to make it work, and we have to simplify the model. So what we did was, well, we set up a number of assumptions, and this slide shows the general assumptions that apply to both the base scenario, which is the traditional fixed route transit service, as well as the AM, right? So essentially, these are the very typical assumptions, made in the literature. But I do want to point out the first two assumptions. So in order to make it an apple-to-apple comparison, because the AMPT is autonomous vehicles, so we also assume the traditional transit service is also using autonomous bus, so that you have an apple-to-apple, because we're comparing the cars. So you cannot have one that has a driver, the other one doesn't have a driver. So the labor costs will be different. So we say, okay, let's take out that. So just assume both are electric autonomous vehicles, okay? And then we also assume that the road infrastructure applies to both systems. So there's no major changes in the road infrastructure, which more or less is true. But obviously, for AMPT to work, there might be some minor modification in the infrastructure, right? So to accommodate the disjoining and joining of the parts, but more or less the infrastructure is the same. But then there's some specific assumptions we have to make pertaining to the AMPT. Okay, so we assume a maximum part chain length, because the part cannot be infinitely joined, right? You have to limit the size. So we assume there is a maximum part chain length. And we're also saying that even though this part train has this very interesting feature of in-route transfer, but we don't assume that all the transfers have to be in-route. So we say that, well, if some transfers cannot be met by the in-route transfer, so you allow people to do the manual transfer, meaning the traditional one, get off the bus, walk to the stop or the same stop and then wait for the next bus to come, and so what we call the manual transfer. So we also assume that not all the transfers will be met by the in-route transfer. Okay, and then the very important assumption about the joining and disjoining is such that, so we assume that joining and disjoining typically happen in the proximity of an intersection or a bus stop. As I mentioned, each intersection is a bus stop. So if you look at this figure, it shows how the joining and disjoining works. So suppose you have two PART trains approaching this intersection or this bus stop, right? PART train A and PART train B. So what happens is after they approach this intersection, PART train A, one of the part is detached from the PART train. And what happens is actually going in this direction instead of continuing in the eastbound direction. So this part, alpha, actually turned and moved to the northbound direction. And then because this PART train B is in the vicinity of this part alpha, so this part can actually join this PART train B. Okay, and that's where the in-route transfer realizes. Okay, so that's what happens. All right, and then we also assume that there's a small amount of delay in the joining, because you have to mechanically connect the parts. So and it has to be slowed down the leading part for the following part to join and so on. So we assume there's a small delay in that, but no delay in the disjoining. So it's simply a detached mechanically. So there's no delay in that case. Okay. So then the way we model it is, well, for the base scenario with the homogeneous demand P1. So we just basically modify from Baganzo's paper to a 2010 paper. So it's a seminal paper for public transit service. So in this model, basically, you have a number of terms in terms of cost. So what they have is essentially it's decomposed into two parts. One is the agency cost, and the other part is asset. So within the agency cost, you have two terms here. So essentially, the first term is the cost of the vehicle miles of travel. So you can look at it as the fleet cost, the size of the fleet, as well as the energy cost for running the fleet. So that's related to the mileage of travel, right? And then the second part is the total operating cost, which is basically associated with the driver's cost. Okay, so the operating time cost. And then for the passenger cost, so essentially there are four terms here in the model. So you have the waiting time when the passenger waits at the intersection or the bus stop, and then the walking time to the bus stop, the in-vehicle travel time, as well as the transfer penalty. Okay, so because most passengers don't like to have more than 2 or 3 transfers. So the more transfers you have, the higher the cost incurs from the passenger's point of view. So this is a very traditional transit model, okay? And there are two dependent variables. One is the number of transit lines. The other one is the headway, right? So to determine the service, the transit service. Okay, so when it comes to the AMPT, the P2 scenario, right, it's also with the homogeneous demand. So there are actually 2 major activities happening at annual stop K, right? One is related to the onboard passenger update. The other one is related to the PART train length update happening at each stop. So let's look at this example. So suppose you have a PART train moving in this direction, approaching this stop K. So if you look at the passenger, what happens is, suppose the current onboard passenger is PK, and then what happens is then you have the passengers that exiting the PART train, right? So this is the people that leaves the train, or they may be they get off so that's the final destination, or they may be transferred to another direction. Okay, the transfer demand here. But there also may be transfer into this PART train from the other lines, the perpendicular lines. So these are the incoming passenger, as well as passengers that are already waiting at the stop to board the POT train, right? So these are the incoming demand. So, and then after this leaving the stop, this will be the new onboard passenger demand inside the POT train, right? So, and in terms of the POT train length, because these are modular vehicles, the size can change dynamically at each stop. So, for example, in this case, originally this POT train has four pots, but then two of them go the other direction, right? One going northbound, one going southbound. And then there's another path from this southbound direction that will join this POT train. So eventually you get three pots leaving this stop. So then you have to update the length of this POT train. So then basically, if you write out the equations, you get this kind of updates. So when you have the incoming onboard passengers at this stop K, after leaving stop K and approaching K+1, that's the new onboard passenger count. And then the length of the POT train. So the original length is the minimum of the maximum POT train length, which we define in the assumption, as well as what's actually the demand for the POT train size, right? And then at each stop, it's updated based on this relationship. Okay, so then another thing that I should point out is also that the in route transfer, the disjoining of these parts actually depends on the dispatching strategy. What I mean by that is, let's look at the typical dispatching strategy for transit vehicles. So this is the beginning point, right, for the eastbound direction and for the northbound direction. So typically for the agencies, all these transit lines, they have the same dispatching time at the beginning of the day, right? So time 0. Okay, all of them will dispatch at time 0 at the same time. Then guess what? This POT train will only meet. So this perpendicular POT trains will only meet at this diagonal nodes. So if you look at the other direction, so they will only meet at those red paths at the diagonal direction. Does that make sense? So that what that means is then you are underutilizing this feature because they can only meet at those nodes other than any other nodes in the network. Then the in-route transfer can only happen at those nodes. Because if the two trains don't meet, the two perpendicular trains don't meet, then there's no in-route transfer, right? So they can only meet at those nodes, then it's underutilized. So with this kind of dispatching strategy. So then we say, okay, let's consider different dispatching strategy to try to improve this utilization of disjoining, and in-route transfer, right? So then we consider two submodels. One is called the P2A, P2P. So for P2A, is this simultaneous dispatching, which is shown in the previous slide, right? So all the lines have exactly the same dispatching time. But in P2B, we say let's optimize dispatching time such that we can have as many transfer points as possible, which is actually shown in this figure here. So you see that if we dispatch the lines in such such a way, so they have a time lag of t0, okay, which is the time it takes to move from one node to the next node or from one stop to the next stop. Then you actually see that all the trains can potentially meet at every single stop. So then that gives the opportunity for in-route transfer or disjoining of POT trains, right? So that's basically the idea. Okay, if we implement this kind of dispatching strategy, then we can maximize the in-route transfer opportunity. So and this can be realized by this dispatching model to maximize the meeting points or the joining disjoining opportunities. Okay, so then we consider these two different models, and essentially we say that modify from the base model, so we can have the new model for the P2A and P2B. So they are very similar in terms of the terms, the cost terms, but obviously the details are different, right? So the parameters and the actual values will be different. But the one thing that I'd like to highlight is the last term. So this is the transfer penalty. So for the P2A, P2B model, so the transfer penalty will be the penalty for only the manual transfer fraction. Okay, for the in-route transfer, we assume there's no delay, right? Because the train don't stop. And so people just move inside the train to do the in-route transfer. So there's no delay for that in-route transfer. So we don't count the penalty for the in-route transfer. Only the passengers who are doing the manual transfer will incur the penalty, the transfer penalty. So then we have to actually determine this, what's called the manual transfer fraction, to calculate the transfer penalty for the P2A and P2B bits. Okay. And then for the heterogeneous demand scenario, so we adopted this kind of monocentric city, the heterogeneous demand distribution. So we say that in the center of the city, the highest demand, and then it gradually decay to the lowest demand other area. And so we basically adopted from Ouyang's paper in 2014, and this is the demand density function, the parameters used in that paper. So we basically just say we just use this kind of a demand function for this type of heterogeneous demand. And then in their paper, the base model P3 is formulated in this way. So essentially, it also had, similar to the P1 model, it also has the agency cost in this one, and then also the passenger cost in this one. So similarly, you have the waiting time, walking time, in-vehicle time, and so on, right? The transfer penalty. So this is the baseline P3 model, and then so we modify this to say, well, all these agency costs and other in-vehicle waiting time, these are very similar, but the transfer penalty is different, right? So we have to determine what is the manual transfer fraction in order to calculate the transfer penalty for the P4 model, right? So, but the idea is similar. So in terms of solving the problem, so essentially this is the solution method we propose, this algorithm. So without getting into the details here, so essentially it has three major parts highlighted in different colors. So essentially it's an iterative process. So within each process, so we let the pod train length go from 5 is the maximum to and go down 5, 4, all the way to 1 pod for the pod train. And then for each pod train length, we calculate the total number of joints and the manual transfer fraction, use some algorithms we designed, and then we solve for the optimum cost function using the Gecko, the solver for that. And then basically we update all these variables, the headway, the pod train length, the number of transit lines, and then see if what we assume is the same as the model derived. And if it's yes, then we update. If no, then we go back and do another round of iteration. Right. So that's the idea. And then we actually ran a little bit of a comparison with the genetic algorithm presented in the literature. So we show that so both of them can produce the exact solutions, but our method is actually 4 times faster than the genetic algorithm. So which proves it's a very effective solution method. And in terms of the experiment, so we assume some parameters, use the same gridded network. So we allow the passenger demand to vary from 0 to 1,000 passengers per hour per square kilometers. And we also vary the network size from 2 kilometer, it's a square grid, to 24 kilometers. And then there's a number of other parameters we adopted from this paper. but I want to highlight because we assume it's autonomous vehicles. So the cost associated with the labor cost is actually 0. Okay, so we assume the coefficients are 0. Remove the labor cost from the equation. So these are the results. So the first one shows the comparison between the P1 and the P2A, which are the homogeneous in that case, with the baseline and the AMPT. So what you see is, if this is the color legend, so it shows that in general, so this is P1 minus P2A in terms of cost, total cost. So in general, P2A does show cost effectiveness over the baseline case, because all the costs essentially show positive. Although in some cases, when the network size is big, when the demand density is high, the cost saving is minimal. It's almost 0. But still, it shows positive cost saving. However, if you look at this corner, for the lower left corner, it actually shows pretty high cost saving. So it can be like 30 to 40% of cost saving. So what is this scenario? So it's when the network is relatively small and the demand density is relatively low. So then you can see this AMPT actually shows pretty high cost effectiveness or cost saving. So this is actually a very interesting finding, because the common sense, the common notion for providing efficient public transit service is you have to have certain population density for the service to be really effective, right? Obviously, we're not talking about making money, but at least you need to have enough ridership to really support transit service. But in this case, when the population density is really low, we typically know that the transit service is not efficient, right? But what's showing here is that this AMPT can actually work very well when the demand density is low, when the network size is small. So think about like this typically in the suburban towns or the rural towns, where you don't really have a lot of people wanting to take transit, but some people, if they don't drive, say they're elderly or they're disabled, they cannot drive or they don't have cars. So this can actually serve very well that population. So that's a very, very interesting finding. And then we further break it down into see, well, for those 30 to 40% saving and the rest of the scenarios, so which one actually contribute the most saving to that 30 to 40%? So it turns out that most of the saving is actually from the transfer, the transfer penalty, because of the in-route transfer by this AMPT. So it actually contribute to about here it's about 40 to 60% of the total saving. And then if you look at the agency's costs, it's actually negative. If you look at a lot of this, in other words, to operate an AMPT from the agency's point of view, it's actually costs more money to purchase the fleet, because it probably needs a bigger fleet and so on. But if you actually look at from the passenger side of people, and it actually reduces a lot of costs in terms of the penalty, the transfer penalty. So that's where the most of the cost saving comes. Okay. So then I guess there's a trade-off from the agency who's running the service. So you maybe invest a little bit more, but the customers will be more satisfied, right? And then this is between the P2A and P2B. Remember these very different dispatching strategies. So it shows that generally speaking, the P2B is doing much better than the P2A, because it can really utilize this in-route transfer feature in the P2B scenario. And then this is between the P3 and P4 for the heterogeneous scenarios. So in general, you see that the cost, it also incurs cost saving for the P4 case, and the energy consumption is also positive. So the P4 case also incurs energy saving, although it kind of stabilized around 60% of saving also, right? But in general, it also incurs cost saving and energy saving. And in terms of load factor, because that's one of the motivations of the study, right? So want to see by using these modular vehicles, do we actually utilize the space or the capacity better? So, and it does show that in both cases, the homogeneous demand case and the heterogeneous demand case, in both cases, so you kind of stabilize at around 20% of load factor improvement in terms of load factor in both scenarios. So that's also a very encouraging finding. Okay. So basically, just to summarize this study. So I don't want to give conclusions because this has, so there's no conclusions, but major findings, summary findings. So really, I think the key findings here is really this AMPT can be potentially very well suited for this low demand density and small network set. Okay, so that's because the general notion is that, well, when you have very low demand, it's not worth providing transit service, right? Because it's very costly to provide transit service. You don't have enough demand to support that. But this AMPT, because of its modularity, so it's more flex in terms of capacity configuration. So it actually makes it more cost effective in this kind of setting. So I think this is probably the use case for this kind of AMPT service. And also the load factor is improved, right? Typically like 20 to 40%. And I do have to acknowledge that at the beginning I show a lot of assumptions, right? So obviously a lot of these are very, very strong assumptions. So all the findings are subject to this assumptions. So in the future, hopefully we can relax some of these assumptions and really make it more realistic scenarios to analyze, right? So I don't know, do I have still have time for the
Yeah, sure. Yeah. So for people online as well, we will have any question either on the line or
so should I don't know, I mean I have this one, but I can save this one. Yeah, we can maybe talk about it. Okay, 5-1. Okay, so maybe I'll quickly go through this. I'm not going to get into detail. So what I talked about so far is the fixed route, the transit service, right? But obviously you can imagine the AMPT, because of its modularity, it probably works better for the on-demand ride-sharing scenario, right? So that's what we also look at in this other paper. And so I do want to, because we already talked about AMVT, so you already know what it is. But I do want to point out for ride sharing. So we actually consider two unique features that can be enabled by this AMVT. One is what we call the opportunistic pod platooning. So basically the pod chain by forming. And the other one is the opportunistic consolidation of passengers. What do I mean by that? So let me just go. So this is the platooning. So essentially you have so basically this is dynamic. So anytime it so happened that these two pods, so if they have passengers already ride sharing in these two pods, origin destination, and at some part of the route, they share a common sections, so they can join if the time allows, right? If they arrive at this point in a very short time interval, then these two pods can join together, form a pod train, what we call the platooning. So the benefit of that is it can potentially reduce energy consumption by forming the tuning, right? So these two pods can join together, and then when it gets to this point, they can depart and go off to their own destinations. So that's what I call the opportunistic platooning. And then the second feature is this consolidation. What do I mean by consolidation? So it's kind of like the second round of ride share. So you already have the passengers ride sharing at the beginning. So these pods will go off and pick up passengers at different locations. But let's say at the last leg of their journey, so they share that they are going to the common destination, and they share the same segment of the route. So guess what happened? So some passengers are already dropping off, and so then you have spare capacity in each of the spots. So then when they come to this point, So then the passengers may be consolidated into one part. And then the other part can be released to pick up other passengers, new demand, right? So that's what we call the passenger consolidation. So the nice thing about this is then you can better utilize the fleet, right? So that's what we call it. So then we consider these two scenarios, and then we model this framework. So we use this what's called the shareability hypergraph to match the shareable rights, and then we look at the energy savings. The objective is to look at the energy saving from this platooning and the consolidation, and then determine the final energy optimum energy saving, most energy saving ride sharing plans. So that's the idea. So this is basically a shareability graph, basically saying that each node represents a request, and if they can be shared based on the constraints of the request, then you have an edge connecting them, right? So these are the, and if there's no edge connecting them, then these two requests cannot be shared. Cannot have share right? So that's the idea. And then we basically use generalize this to a hypergraph, right? It can be more than one node at each edge, each vertices. And and then we just basically model this, and we give certain constraints for the passenger has pickup time constraints, and then the drop-off time, the delay, right? So the detour cannot be too long, so passengers will not be happy about that, right? So basically, then we formulate the problem to basically saying that, well, you have the total energy consumption of the whole route, but then there might be a savings from the platooning and savings from the consolidation of passengers. Okay, so then we're trying to minimize this total energy consumption of each ride sharing trip, and then we basically look at a hypothetical scenario with this kind of network, right? It's different OD pairs we've assumed. So I think the maximum is assume 100 OD pairs within 5-minute interval, and then essentially we see that there's energy saving compared to the baseline where there's no ride sharing, okay? And so the energy saving goes anywhere between 5% to 30%. But the interesting thing here is that what we found out is, this is actually probably the most interesting finding, is that within the energy saving I showed from the previous slide, most of the energy saving is actually coming from the ride sharing itself. Very, very little from the platooning or the consolidation. So what does that mean? That means that probably we don't have to really consider this platooning or the hot train joining, disjoining, or the consolidation of passenger, because the benefit is really small. Mostly is coming from the ride sharing itself. But this is a very small experiment. We only consider 1 5-minute period with up to 100 passenger OD pairs. So that's we're actually conducting a bigger, more dynamic. So this is a static case. So consider a dynamic scenario and bigger size network to really see if this is indeed still the finding we have. Okay, so I think that's basically what I had, and this is the last slide. Thank you very much.
Does anybody have a question?
Yes.
So it really makes sense in the beginning where certain climate is more ridership, it will not be climate is less ridership in a certain route. So imagine in a local bus city bus case, they change the bus sizing, right? They have multiple, they have like 3 different bus sizes, and during their peak hours, they'll give a longer bus compared to off peak hour where they have a shorter bus. So if you include such the cases in your cost function, I guess.
For the base case.
Yeah, for the base case. Then would the results still it is
It will still be this case. So the reason for that is in the typical transit operations, like for example for CTA in Chicago, so there are 2 types of buses. One is the 40 seat, that's a single bus, and the other one is called the articulated bus, which is about 60 to 80 seat. So wide. Yeah. So these are either 40 seat or the 60 seat. In most cases, other than the peak hours, so it is pretty well utilized during the peak hours in Chicago, I must say. But the rest of the day, those buses that you see, like only a few souls in the bus. So 2 or 3 people sitting in the bus. Even with a 40 seat bus, that's a